the basic comparator is just a high gain element which is being used open loop and whose output is regarded as a digital signal. Comparators often have differential inputs, which means that the function would look like this. We have two input voltages and the output is a logic function which tells you that what is true when the positive input is larger than the negative input. The simplest way to make a comparator is simply to use an op-amp without compensation. Now the reason you don't want the compensation is that it slows down the circuit, and since the comparator is used in open loop, you do not need to have it in there. Now, for instance, think of an application where we have a 16-bit audio signal. So audio signals are normally sampled at 44 kilohertz. And if we were to implement the circuit which digitizes the audio circuit, we might use a successive approximation ADC, which we will have a look at later, which would require 17 samples to process 16 bits. Now that would mean that the time available to process one bit would be equal to the sampling rate times 17 bits to the minus first, which corresponds to a bandwidth for the circuit of 748 kilohertz. Now to have a 16-bit ADC, we would need to have a comparator that can tell if the two inputs are similar within half a bit resolution. That would mean that it would have to have a gain which is 2 to the 17th or 102 dB. Now this is a very high gain for an integrated circuit. Now what is also important to know that if we look at the gain bandwidth product here, that would result in 98 gigahertz. Now this is an extremely high frequency, certainly for something that is processing just a fairly conventional 16-bit audio signal. And this is really highlighting why we can't just use an op-amp as a comparator, because in most but the really slow cases it would simply not have the speed. It might have the gain, but it will not both have the gain and the speed. So here we have, for instance, a conventional continuous time comparator, which is just the op-amp circuit we have been looking at earlier, where the compensation network has been removed. Now, since the comparator would normally drive digital gates afterwards, it is quite common to put a buffer stage on the output of a comparator. Now, such a buffer stage would often be just a conventional digital inverter, and the reason it is an advantage to use this is that the load capacitance at the output here would then be just a single inverter stage, and that would mean that it will speed up the comparison process. It also gives extra gain because the digital inverter do have gain, and you can even have as many gain stages as you like and have as high gain as you desire. Because you're not using it in feedback, it is possible to have as much as you like without any stability issues. Now if we have put in one digital inverter state like that, that would mean of course that we have now swapped what is a positive and negative input. So in this circuit the right hand is the negative input and the left hand is a positive input for this whole circuit here. What we have assumed here with putting in the digital inverter is that it is running on the same supply as the analog circuit, which is not necessarily the case, but it could be. Now, as for the normal op-amp or any other amplifying circuit, we can apply a PMOS differential pair as done here, or we could take a mirror image of the circuit and have an NMOS differential pair just as we did with the op-amp. Again, the main consideration here is probably about what input voltage levels are required. And since the input circuit is really identical to the op-amp circuit, the input voltage range would be the same as that for an op-amp. Now, if we have the situation where we have different analog and digital supply voltages, we will need to make sure that in the bias condition for the analog gain stage, that would sit somewhere in the mid-range for the digital, or in the transition region for the digital inverter. Now, if we have, for instance, a 1.8 volt power supply, then the expected value for the output of stage 2, so V out 2 in the bias condition, would be round about, let's say, 0.9 volt. This would be a reasonable expectation. Now that might be okay to feed directly into a digital gate, but that would be quite skewed. It's quite likely then, if the digital is 1.2 volt, that this would be regarded as a high at the input there rather than a mid-range, which would then create an offset. So making sure that the biasing is good is one consideration. Now we could perhaps putting in a source follower like this at the output stage, just to lower the voltage, because it would drop down by around about half a volt. We would need to have another bias transistor sitting in here with another bias voltage if we use an in-source follower, so VB2, and in which case we would have the bias condition of this one here being around 0.4 volt, which is closer to the sort of ideal level of 0.6 volt at the input there. But the detail of such a design really depends on the process and how to get from the analog side to the digital side if the power supplies are not the same.